All right, this is the solution for the fourth problem in the discrete time section for the final exam review. Okay, in class I talked about how I thought, or I think, every engineer should know about the A to D conversion process. Okay, where we start with a continuous time signal and we end up with a discrete time signal, which is the continuous time signal evaluated at every cap t sampling time. Okay, so to fully understand this, I also want you to be able to draw a diagram. Okay, so let's make a time axis and a vertical axis. All right, so here's our time axis. All right, I really should center that up, so let's go with that. And then what I want to do is make a representative signal. All right, so here's an analog signal. It's doing something. Oh, that's not very good. Let's try again. Let's make the line a little thicker as well. Here's an analog signal. All right. And I want you to be able to tell me what the sampling portion represents. Okay, so this is the time axis. Okay, put that in green. This is time. And what we're doing with sampling is we're actually chopping up the time axis. Okay, so I represent that with vertical lines. Okay, so equally spaced apart by cap t. Cap t is the sampling period. Okay, so we draw a few of these vertical lines in to represent sampling. Okay, so in the problem statement, I wanted you to be able to identify what the sampling portion of the A to D conversion process is. Well, this is it. Okay, so all these are spaced apart by cap t. All right, and then we sample. Okay, so the red dots would indicate ideal sampling. Okay, but what I also want you to know is that in the A to D process, it's not perfect. Okay, we can't have a continuum of outputs and still represent that with a discrete number of bits. All right, so in this particular case, I'm going to chop up the vertical axis into, let's use orange, into 8 levels. Okay, so let's start about right here. That's crooked. So let's just start over. One, 2, 3, and 4. There's 4 levels on the positive side, and then 4 levels on the negative side as well. They're supposed to be equally spaced, but you get the idea. Okay, you can adjust those where they would be equally spaced. The A to D conversion process gives me samples that I'm going to show in purple. They're not the red dots. The red dots would be perfect quantization. So this particular vertical axis is where the quantization part comes from. Okay, so it's quantized to a certain number of output levels. All right, so if I'm looking at this red dot is closest on the grid to right here. So that's the output level that would actually be represented. Notice it's not perfect, and that's why we have what we call quantization noise. All right, so in this particular case, I have 8 output levels. 8 output levels is equal to 2 to the 3, so 3 bits. All right, if I had 16 output levels, how many bits would that be? 2 to the 4th, so it would be 4 bits. So generally we have a lot of levels. It's not unusual to have 16 bits. So that'd be 65,000-ish levels. Okay, so by the time you get that many levels, the quantization error is really pretty small. Okay, but finishing this off, you choose the closest point on the grid at every time sample. Okay, and then next, I'm going to use this off red. Next, you would have a code that represents each output level. So maybe I would say, here is 0, 0, 0, here's 0, 0, 1, 0, 1, 0, 0, 1, 1, and here's 1, 0, 0, 1, 0, 1. All right, so here's a code that represents each output level. All right, so from here I can number these samples just to make it easier. Here's 1, here's 2, here's 3, 4, 5, 6, and 7. So we have 7 output codes that are represented in the A to D conversion process. Okay, so the first output maps to 0, 0, 1, so we can write that down. The next one maps to 1, 0, 1. The third sample here maps to another 1, 0, 1. The fourth sample maps to 0, 0, 0, and so forth and so on. Okay, so from an analog signal, so here's our analog signal, we converted that to a sequence of numbers, binary numbers, and so that's how you end up with digital A to D conversion. So in summary, here was the sampling axis. So the vertical lines represent sampling, the horizontal lines represent quantization. Another part of the problem is I asked, how fast do you need to sample? Well, how fast you need to sample depends on how fast this signal is changing. Okay, so a measure of that is the signal's bandwidth. And so I think everybody had told me that they were familiar with the sampling rate needs to be at least 2 times the maximum frequency. All right.